Okay, welcome to EGR 550. In today's class, I'm going to focus on a couple of things. First, we will discuss something called as the linearization. We will also talk about mathematical modeling. And at the end, we are going to look at the temperature control lab. So again, I just want to make sure that everyone was able to get some data from the temperature control lab. Any questions, concerns? So in last class, we talked about the single heater. I did not talk about in detail the theory and the mathematical model behind the single heater, but I wanted you to get some hands-on experience before we start discussing. So in today's class, once we are done with the theory part of the lesson and we proceed to the actual experiment, I will briefly talk about the single heater lab modeling. And I will also talk about how we can run that simulation using MATLAB. And I know some of you already uploaded the lab report. That's fine. But what I want to talk about is I would also show you the results of the single heater simulation inside the MATLAB. So, and then if you like, you can compare the experimental results with the theoretical results. But before we move on to the lab, let's talk about what we started discussing in last class. In the last class, we talked about the mathematical modeling of dynamical systems. We also looked at the state space representation. We also looked at how you would do a state space representation when you have a single input, single output system. So an example here is you have a spring mass system. The output of this system is displacement, and the input to this system is the external excitation. So this system is a single input, single output system, or also called as SISO system. Now what I want to do is I want to extend this to something like what would we do if this system is multiple input, multiple output, or Mimo system. So I just want to talk about a case wherein that we have this mass attached by a spring. This mass is attached to other spring. And then finally, the second mass is attached to the support. So support is fixed. The stiffness of the first spring is K1. Stiffness of the second spring is K2. Stiffness of the third spring is K3. Now we have M1 as the mass of the first mass, M2 is the mass of the second mass. And what I want to do is I want to derive the differential equation of motion for this Mimo system. Why is this called a Mimo system? Because if you think about it, you can have U1t, which is the excitation on the first mass. You can have U2t, which is the excitation on the second mass. And then we will have two displacements. So for an example, we are going to have the displacement of mass M1, which is x1. We'll have displacement of mass M2, which is x2. Now we can derive this differential equation using energy technique, or we can derive this equation using the Newton's second law, which is summation of forces is equal to mass times acceleration. Force is a vector, acceleration is a vector, which means it will have magnitude and direction. Mass is a scalar, which means it will not have direction, it will only have magnitude. I'm going to start with a simple assumption: x2 is greater than x1, and I'm going to set up my coordinate system something like this. So the motion in the positive x direction is going to be positive. So what's going to happen is mass m2 will be pulled by the distance which is greater than the distance mass m1 is pulled. So if you think about it, I'm going to draw the free body diagram. This is mass m1. As I stretch this spring, there will be the force which is k1 x1, and please understand there is this another mass which is m2. This m2 is pulled towards right hand side, so there will be the external spring force k3 times x2. Now what I want you to understand is x2 is greater than x3, which means k2 is actually stretched. So when k2 is stretched, k2 is going to pull this mass something like x2 minus x1, and k2 is going to pull this mass k2 x2 minus x1. So please understand that what we have is we have three springs, k1, k2 and k3. K3 is compressed, k1 is stretched, and k2 is stretched because x2 is greater than x1, and this is the assumption. Okay, this is the assumption. Now let's look at the displacements. So the acceleration is in this direction, the acceleration in this direction. So I'm going to apply Newton's law to mass m1. So summation of forces is equal to mass times acceleration. So forces that are going towards the right hand side are considered positive. So if you look at the forces, they are going to be plus k2 x2 minus x1 minus k1 x1. The acceleration is in the positive direction, so that's going to be m1 x1 double dot. So this equation can be written as m1 x1 double dot minus k2 x2 minus x1 plus k1 x1 is equal to 0. I will try to simplify this. I would say m1 x1. Then as you can see, this is going to be k1 plus k2 x1 minus k2 x2 is equal to 0. I'm going to call this equation 1. And since there is an external force here, I'm going to write this external force something like u1 of t. Now let's look at the second mass, which is summation of forces is equal to mass times acceleration. And let's look at the forces. K2 x2 minus x1 is going towards left hand side, so this would be minus k2 x2 minus x1. K3 times x2 is also going towards left hand side, k3 x2, and I have, this is x2, so m2 x2 double dot. So this equation can now be represented as m2 x2 double dot plus k2 x2 minus x1 plus k3 x2 is equal to 0. So I will rewrite this equation. So this will become m2 x2 double dot plus, please note, k2 plus k3 x2 minus k2 x1 is equal to u2 of t. So everyone understood that equation 1 and equation 2, they indicate the Mimo system, multiple input, multiple output. Again, why this is a multiple input? Because there are two inputs, U1 and U2. And why is it called multiple outputs? Because there is X1 and X2. So you have multiple inputs, multiple outputs. Now, how do we solve these equations? Now, what I'm going to do is I'm going to rewrite these equations in a matrix vector form. So what do I mean by matrix vector form? So I'm going to write these as a mass matrix multiplied by the acceleration vector plus stiffness matrix multiplied by the displacement vector and then external force vector u of t. So I want you to look at the equation that I wrote and tell me, how do I fill in these blanks? So this mass matrix has 2 by 2 structure. Stiffness matrix also has 2 by 2 structure. And this forcing vector also has two elements, u1 of t and u2 of t. So now what I want you to do is tell me what would be in first row, first column, first row, second column, second row, first column, and second row, third column, second row, second column, sorry. Any suggestions? You're welcome to enter that in the chat window, or you're welcome to M1. Okay, so this will be M1, 0, 0, M2. Here, K1 plus K2 minus K2 minus K2, K2 plus K3. So if you multiply these two, then finally you would get these equations. So can you just check and let me know if that makes sense? Are you with me so far? You want me to expand this, or you guys are good? Okay. Now this is the equation in matrix vector form. Now, how do I solve this using the techniques that we discussed in last class? Say if I want to use MATLAB, what I want to do is I would like to, and this is super important. If I want to solve this system using MATLAB, I need to write this into a state space form. State space form. In state space form, there are following states. There is x1, x1 dot, x2 and x2 dot. So x1, x2 dot, x1 dot, x2 and x2 dot. So if I want to express this expression into state space, what I need to do is I need to write this expression something like this: d by dt x1 x1 dot x2 x2 dot is equal to a matrix which is A x1 x1 dot x2 x2 dot plus I'm gonna have a B matrix, and then there will be 0 u1 0 u2. So this can also be written something like this. You can have u1 u2 and you can have this B matrix something like 0 1 0 0 0 0 0 1. First row, actually not like this. First, so basically this will be 0, first row, first column, so it will be 1 0 1 0, and then this will become first row, first column, so this will become 1, yeah. So this form is good enough. So you can write this in this form. You can actually take these zeros and make those part of matrix B, and then you can write. So what I was trying to do is write this something like B times u1 u2. So and then make sure that your final answer is 4 rows, 1 column. So this needs to become like u1 u2, and this will be 1 row, 2 columns. So this will be 4 row, 1 column. I made a mistake somewhere, so let me see. 4 row, 1 column, u1 u2, 1 row, 2 column. So right, so this will become something like this. So this is gonna be just this will be something like 0 u1 0 0 plus 0 0 0. It would be something in this form. So you can try to do this math, but at the end we should get the system which is shown over here. Okay, that being said, now I will rewrite the terms here. So this will become 0 1 0 0. This will become 0 minus K1 K1 plus K3 divided by M1. Then this will be, actually I don't have enough space here. I'll rewrite in the next slide. So this will become d by dt x1 dot x2 dot is equal to x1 dot x2 dot plus 0 u1 0 u2. This will become 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. So this will become 0 1 0 0. X1 dot is equal to minus K1 plus K2 divided by M1. Then this will become plus K2. This will become 0 0. This will become 1 0 0 0. And for x2, this is going to become plus K2 0 minus K2 plus K3 divided by M2 0. Now please check if my math is correct. And then so see if there is anything I'm missing. So this is x dot is equal to a x plus b u. Ax plus bu. And then y is equal to cx plus du. Usually this d is 0, assuming our output. So the state vector is not going to change. x1 dot, x2 dot. So the state vector is not going to change. So this will be 0. So this will be 1 0 0 0 0 1 0 0 0 0 1 0 0. Oh yeah, sorry. So what that means is my y vector output is going to be x1 dot, x2 dot. This is going to be my output. So this is how a multiple input, multiple output system should look like. Any questions here? Any questions here? So, and you can use this for simulating it inside the MATLAB. Now, there is one important part that I want to talk about, and that involves basically D is the coupling between the controller input and the output, and very rarely you would see a coupling between the control input and the output. So usually the control is separate from the output. That's why the typically D matrix is 0. I mean, in very rarely you will see a non-zero value of D, because in what that means is you have some type of effect. I mean, the external forcing is changing the output, but that happens very rarely. That's why typically the value of D is 0. Now what I want to do is, I just want to give you how would you solve this typical problem using Laplace transform. So I want you see how would you do it with a Laplace transform. Now please understand, so we have this Mimo system, multiple input, multiple output, and we want to do the Laplace transform, or other way to say that is find transfer function. Transfer function is the Laplace transform of output divided by the Laplace transform of input. Now here is the challenge. Since it's multiple input, multiple output, we have U1, U2, and we have X1 and X2. Now the question is, and I want you to think about this question very, very carefully. What should I select as input and what should I select as output? And I am looking for some answers. So tell me, what should I consider as input and what should I consider as output? Now here is a trick. When you do the Laplace transform, you cannot have two inputs in the numerator and two inputs in the denominator and two inputs in the numerator. It has to be a single pair. Okay, what does that mean? And we'll work this problem out in detail. So what does that mean? Which means I can select a pair which is something like this. That's perfectly fine. So I can say transfer function wherein I have x1 of s divided by u1 of s, and we can find out a transfer function. Nothing wrong in writing the transfer function for the second pair. So this is my transfer function 1. I can have a transfer function 2, which would be x2 of s divided by u2 of s. That's fine. But this is also acceptable. So what that means is I can do u1 and x2. So transfer function 3 is x2 of s divided by u1 of s. And clearly there can be a transfer function 4, so which is something like u2 and x1. So you can have transfer function of 4 is x2, so x1 of s, x1 of s, and u2 of s. So these 4 transfer functions are possible, and each transfer function is important because let's understand what they mean in terms of the physical system. So our physical system is like a 2 mass 3 spring system. Now this is x1, there is u1, this is x2, there is u2. Now the first transfer function is going to tell me how the response of the first mass responds to the force on the first mass. Okay, because if you look at the input is u1 and output is x1, so it's basically relating the forcing on the first mass to the output of the first mass. If you look at the second transfer function, it is going to relate input on the second mass to the output on the second mass. So you basically, it is like x2 and u2. Third transfer function is relating, this is very interesting. Third transfer function is relating input on the first mass to the response of the second mass. Input on the first mass to the response of the second mass. And the last transfer function is representing input on the second mass. How does that affect the response of the first mass? Everyone understood this? So every transfer function is going to give us key input or key insight into this mass. And I want you, I mean, believe it or not, this is true. You can tune, and this is the principle of essentially tuned mass dampers or vibration absorbers. So what is a vibration absorber? Vibration absorber is an auxiliary mass that is attached to the main system with a single purpose. If the main system starts vibrating, this auxiliary mass would capture its energy. So in other words, you attach this auxiliary mass to the main mass, and if there is oscillation of the first mass, basically there is a coupling between the second mass, and the first mass stays stationary, but the second mass starts vibrating. And this is a fantastic phenomenon to observe. So what it means is you have a vibratory system. So T3 and T4s, T3 and T4. No, they are not imaginary. They actually, that is how you derive the transfer functions for absorbers. So again, what is the concept? You have this primary mass. This primary mass is going to vibrate. What you want to do is, you don't want that primary mass to vibrate. So what you do is, you add an auxiliary mass to the primary mass and tune the transfer function in such a way that, or tune the spring stiffnesses in such a way that all the excitation that is inputted on the first mass get transferred to the second mass. And that is how you quench the oscillations of the first mass. And basically this is used in design of vibration absorbers. So I'll show you, let me derive these transfer functions, and then this all will make sense. So let me derive these transfer functions. So very quickly, what I'm going to do is, I'm going to rewrite the differential equations of motion. Differential equations of motion are m1 x1 double dot plus k1 plus k2 x1 minus k2 x2 is equal to u1 of t. I'm going to take the Laplace transform. So what are the rules for Laplace transform? My independent variable t gets converted to independent variable x. My x1 of t gets converted to capital X1 of s. My x2 of t gets converted to capital X2 of s. If I have x1 dot, that's it converted to s times x1. If I have x1 double dot, that get converted to s square x1 of s. Are you with me so far? K is a constant. K1, K2, K3, they are all constants. So they won't change. And U1 of t gets converted to U1 of s. So I'm going to make these changes. So M1 s square x1 of s plus k1 plus k2 x1 of s minus k2 x2 of s, u1 becomes u1 of s. Are you with me so far? Everyone with me so far? Now what I want to do is, if I want to now check this out, I'm gonna do the same jugglery for the second equation. I'm gonna say m2 x2 double dot plus k2 plus k3 x2 minus k3 k2 x1 is equal to u2 of t. Are you with me so far? Same jugglery. M2 s square x2 of s plus k2 plus k3 x2 of s minus k2 x1 of s is equal to u2 of s. So capital U2 of s. So the equations that I should be looking at is this equation 1 and this equation 2. Now let me start with the first transfer function. So my first transfer function tf1 is x1 of s divided by u1 of s. Are you with me so far? So I have equation 1 and I have equation 2. Now you please tell me, how should I proceed? Do you agree with me? The easier way seems to me like I can start with equation 1. I can start with equation 1 and I can try to combine x1s on one side. So this equation is going to be, look at, carefully follow equation 1, and this equation can be written as ms square plus k1 plus k2 x1 of s minus k2 x2 of s is equal to u1 of s. Do you agree with me? So now what I have is, I have x1 that needs to go over here and I have u1 that needs to go over here. But unfortunately, I have this x2 that is floating around, that somehow I need to eliminate. Are you with me? Because the transfer function is relationship between a single input and a single output. My single input is x1. My single output is u1. But when I look at the differential equation, since this is a Mimo system, multiple input, multiple output, the second output is floating around in that equation. Do you agree with me? Now the question is, how do I eliminate that x2? We can't assume x2 is equal to 0 because x2 is going to affect the dynamics. But what we can assume is there are different ways of assuming, but different way you can assume this. What I can do is I can eliminate x2, using equation 2. So how do I eliminate x2 using equation 2? So if I want to eliminate x2 using equation 2, what I'm going to do is I'm going to write this equation something like this: u2 of s plus k2 x1 divided by m2 s2 plus k2 plus k3 is equal to x2. Are you with me? This comes from this equation. Everyone understood this? So I want you to look at the second equation, and I'm trying to eliminate the value of x2. So please understand, using the second equation, x2 is now represented in terms of x1. Do you agree with me? So this whole equation, now the whole equation which is over here, can go in here, and u2 is the forcing on the mass 2. And what we want to do is, you can't have too many unknowns. Either u2 must be completely known. It could be like sine, cosine, whatever the term is. u2 must be known in the closed form, or u2 can be 0. So this expression u2 must be known in closed form. So u2 can be a sine, cosine, or it could be 0. But then what would happen is, when you combine these two equations, the only two terms that would be floating around are going to be u1 and x1. Everyone understood this? When you substitute this equation 3, actually I'm going to call this equation 4, and I'm going to call this equation 3. So when you substitute equation 4 in equation 3, the only terms that will be floating around are x1 and u1, and you should be able to take the ratio and find out the transfer function. Everyone understood this? Online students, any question? So in Mimo systems, that is how you can eliminate and find out the transfer function. Now, the story doesn't end here. So with this mathematical jugglery, we were just able to find out the first transfer function. we will have to do the exact same mathematical jugglery to find out the second transfer function. We have to do the exact same mathematical jugglery to find out third transfer function. And we have to do the exact same mathematical jugglery to find out the fourth transfer function. Are you with me so far? Everyone understood what's happening with the transfer functions? I mean, you will have to work this out. Only then you will understand. And I'm going to give you a homework today so that you will have some practice on doing this mathematical jugglery. And then this will give you a tremendous insight into what's happening with a dynamical system. So what does that mean? Now, so it means, let's understand what is the physical meaning of transfer function. Transfer function is Laplace transform of output divided by Laplace transform of input. This transfer function is going to have a numerator, and this transfer function is going to have a denominator. Okay, so I can write down this equation something like output is equal to transfer function multiplied by input. So I will write this down something like a numerator and denominator multiplied by input. So think about a transfer function. Transfer function has a numerator, transfer function has a denominator, and you are going to multiply that by input. Now I want to ask you one case. For some reason that is unknown to us, if the numerator is 0, for some reason that is unknown to us, if numerator is 0 or becomes 0, what does that mean in terms of output to input relationship? What does that mean in terms of output to input relationship? For some reason, if the numerator of the transfer function is 0, what that means is no matter what your input is, your output is going to be 0. Everyone understood this? So in other words, if the numerator of the transfer function becomes 0, then the output becomes 0. Everyone understood this? And that is the condition we call as zeros. So when the numerator of the transfer function, becomes 0, that we say we are finding the zeros of transfer function. But what does that mean physically? And this is very, very important concept when you design a mechanical system. Imagine what you want to do is all of a sudden you want the output of the system to be 0. Imagine, I give you a hypothetical example that you are driving a car and you want your control system to behave in such a way that for particular input or for particular operating condition, no matter what input driver provides, the output of the control system has to be 0. What would you do is you will design the numerator of the transfer function in such a way that for that particular operating condition, the numerator of the transfer function is 0, which means no matter what happens on the input side, the output of system is going to be 0. Everyone understood this? What does it mean in terms of absorbers? So what you do is you have an absorber and you tune the numerator of the transfer function in such a way that for particular frequencies, for particular gain values or particular operating condition, that numerator of the transfer function becomes 0. What that means is basically that machine even though it is subjected to some unbalanced forces, will not vibrate. Everyone understood this? Now, next thing what I want to ask you, imagine a case where the numerator is non-zero, but the denominator is zero. Somehow, the transfer function denominator becomes zero. What does that mean for the output? Output will become infinite. Do you agree with me? So no matter what the input is, whether the input is extremely small, because the denominator of the transfer function is zero, the output will be unbounded. What is the application of that? Amplifiers. So if you have a mechanical amplifier, or if you have an electrical amplifier, or if you have an electronics amplifier, and what you want to do is you want to magnify this teeny tiny motion. It could be the motion of the diaphragm. You talk into mic, and then basically the motion of the diaphragm is very small, but that electrical signal needs to be amplified. Then whatever the transfer function of the system that you have needs to have the zeros, or basically the denominator should become zero, and then automatically that output will be magnified. Do you agree with me? Or what you want to do is you want a recoil mechanism. Say for example, you are launching a projectile, and what you want is you want to give a teeny tiny input, but you want that teeny tiny input to be converted into a very large propulsive force onto the projectile. So what you will do, you would actually tune the transfer function of that launcher in such a way that teeny tiny input gets fed into the transfer function that has zero denominator, which means the output becomes infinite. In theory, in theory it says infinite. In practice, it's very large. Everyone understood this? Another application is MEMS systems. So MEMS are micro electromechanical systems, accelerometers and gyros that are used in smartphone. So what you want to do is you want to trigger the sensing element, even though there is motion which is teeny tiny. So you tune the transfer function for the sensing element in such a way that extremely small movement is captured, because the transfer function denominator is zero, and you get very high amplified output. Everyone understood this? So when the denominator of the transfer function is zero, we call it as the poles. So denominator of the transfer function is zero, we call these poles. Everyone understood this? Any questions here? So remember this, and now I want you to actually work out these transfer functions, and that will give you some insight into the system behavior. Now let me give you a very practical application. The practical application is tuned vibration absorbers. So now tuned vibration absorbers, so you have this primary mass. Okay, this primary mass is attached on a spring, and you notice that this primary mass vibrates, but you don't want this primary mass to vibrate. So what you are going to do is you are going to attach a teeny tiny auxiliary mass with spring and damper. You are going to attach a teeny tiny, so this is capital M1, this is small m2, this is capital K1, this is small k2, and this is small c2. So you are going to attach this teeny tiny mass onto this big mass m1. and you are going to tune this spring. So tune this spring and this damper. So tune K2 and C2 such a way that motion of M1 is minimized. So what that means is you have this U1 of t, you develop a transfer function in such a way that x1 divided by u1, you will have a transfer function. Such a way, you will design this transfer function in such a way that this numerator becomes 0. And what would do this is you will tune K2 and C2 in such a way that this numerator becomes 0.
Can we multiply by 0?
You can't multiply so you want to have the system parameters in such a way that they effectively make it 0. You cannot add 0 to transfer function. So basically what you want to do is you want to tune the system parameters, adjust those system parameters in such a way that the numerator becomes 0. And again, this is just I want to give you a little bit idea. There is, literature, significant amount of literature on how to design the tuned mass damper systems. You can use linear spring, you can use nonlinear spring, you can use single mass, you can use cascading mass, you can change the geometric configuration that changes the coupling coefficients K2, or you can use some type of an electromechanical coupling that will change the stiffness and the damper and then achieve this vibration isolation. Okay, any questions here? But this is a very fantastic field, and actually I will give you a couple of homework problems at the end of today's class that will give you some insight into tune mass damper system. Any questions from my online students? Okay, next part which I want to talk about is, we talked about the properties of the state models. We looked at the principle of superposition, which means x1 plus x2 or u1 plus u2 is equal to x1 plus x2, which means if u1 is causing response x1, input u1, so let me just write down for my own satisfaction. If u1 is causing y1, if u2 is causing y2, if I simultaneously apply u1, u2, I'm going to get y1, y2. Now, very rarely we see linear systems. Majority of the systems that we see in practice are nonlinear systems. So what are nonlinear systems? One burger for $1, two burger for $2, but 5 burgers for $3. It's a nonlinear system. So for an example, a very simple application of a nonlinear function or a nonlinear system is a sine function. So if you look at the sine function, this is not a straight line. This is a curve, which means this is nonlinear. A simple dynamical system that we have studied a lot of times is this pendulum. You have this mass, this is the length of the pendulum, and if you look at the equation of motion, this becomes ml square theta double dot plus g sine theta is equal to 0. So ml square theta double dot which is mgl sine. So I'll write mgl sine theta is equal to 0. So this equation becomes theta double dot plus uh, g over L sine theta is equal to 0. This equation, it looks very simple, but it's a nonlinear equation. Everyone clear how this equation came into existence? Just for my own satisfaction, let me just quickly derive this. So we had, this is the pendulum. This is the mass. This is L. If you look at the gravitational force, mg, this distance is L sine theta. Newton's law, its force is equal to mass times acceleration in the translational coordinate, and this can be written as T is equal to I times alpha in the rotational coordinates, where T is the torque, I is the mass moment of inertia, which is mass times the radius of gyration square. Radius of gyration square. Now, what I'm going to do is, if you look at the torque, there is gravity, the weight m times g, L sine theta. This torque is in this direction. So curl your fingers in the direction of the torque and you will notice that this torque is positive. This is m L square theta double dot. So you will write this equation m L square theta double dot plus m G L sine theta is equal to 0, and this is the equation. This is the dynamical equation of motion. And I presume that you have seen this equation before, right? Now, what do we do at this point? Sine theta is basically a nonlinear function. So sine theta is a nonlinear function. But what we assume that in this teeny tiny region, sine theta can be represented as a linear function. So this is the region wherein sine theta behaves like theta in radians, and that is actually true. If you don't believe me, I want you to check this. Do sine 17 degrees and equate it to 17 divided by 180 multiplied by pi in radians. So quickly, if you do this calculation, you will realize that as long as the theta value is less than 17 degrees, the left hand side of this equation is equal or close to equal the right hand side of the equation. So what we say is, for small angles, sine theta is equal to theta. And we have seen this classic equation, ml square theta double dot plus mgl theta is equal to 0, or theta double dot plus G over L sine theta is equal to 0. Are you with me so far? And please note, this equation is nonlinear. And this equation is linear. Are you with me so far? Why the first equation is nonlinear? Because sine theta, this function, is nonlinear. Why the second equation is linear? Because theta is a linear quantity. So it's like 1, 2, 3, 4. It's not like the nonlinear functions. Everyone understood this? Now, couple of observations. This linear approximation is valid in a very small operating range. Are you with me? This linear approximation is valid in a very small operating range. If that operating range is beyond the initial approximation valid range, then this approximation is no longer valid. Now, here is the reason why. Have you seen those old grandfather clocks? And they have a pendulum at the bottom. Have you noticed that that pendulum is going down or going forward and backward with a very small angular displacement? You will never see that pendulum going down like this, because then the period is not linear. Period becomes non-linear. So if you see those old grandfather clocks, if you look at old grandfather clocks, there will be stops. There will be physical stops here. So this is the clock, and this is the pendulum. And then you will notice that there will be physical stops on the either side of the pendulum to prevent it from going outside the linear region. And as long as this is in this small region, everything is fantastic. You will get a very accurate representation of time. So the process, now this is very important, the process of taking this nonlinear equation and converting into a linear equation, this process is called as linearization. Once again, what is linearization? You have this nonlinear system of equations. You are converting this into this linear system, and that is called as the linearization. Why is linearization important? The linearization is needed because we can solve linear equations in closed forms. So we know everything about the linear equations, but we don't know a whole lot about nonlinear equations. Nonlinear equations can exhibit super complex behavior. They can exhibit something called as the bifurcation, which means the response changes depending upon the amount of forcing that you apply. The response could become chaotic, which means the teeny tiny change in the initial condition will give you totally different results. So nonlinear systems exhibit super complex behavior that sometimes is not good for application. Imagine you have a grandfather clock and it does not describe the time, or it does not tell you the accurate time, because sometimes it's fast, sometimes it's slow. That clock is not going to serve any purpose. So we want that clock to operate in a linear region. And how do we make sure that the clock is operating in the linear region? Is by limiting the oscillations of the pendulum. And this process of taking this nonlinear system of equation and converting into this linear system of equation is called the process of linearization. And how do we linearize? We linearize using some sort of approximate technique, which could be a Taylor series approximation. And what I'm going to do is I'm going to stop here. We'll take a break of 15 minutes. And after that, we will come back and I will work out, I'll give you details on the linearization, practical applications of linearization, and then we will perform the labs. So I'm going to stop here. Okay, so now the question we are trying to think about is how do we linearize? So here is what the linearization means. The real systems are nonlinear, and usually these nonlinear systems are represented by nonlinear equations. So a classic example is, so if you have a spring mass system, and we have been talking about this a lot because this is a basic component. So this equation is mx double dot plus kx is equal to 0. This is a linear system. Now imagine if I have a nonlinear spring. So what I have is, I have this nonlinear spring. So a linear spring means the resistance of the spring is linear with respect to the displacement. So force versus displacement relationship is linear. If you have a nonlinear spring, then maybe the force versus displacement relationship for the nonlinear spring is nonlinear, and the equation of motion would become mx double dot plus kx cube is equal to 0, or maybe mx double dot plus kx square is equal to 0. So this is a nonlinear equation, and this is a linear equation. Linear equations are easy to analyze, they are easy to solve. Nonlinear equations, on the other hand, they are complicated. Now, how do we linearize this nonlinear system? And the easiest way to do the linearization is something called as the Taylor series. And I want to actually give you the geometric view of what Taylor series is. Imagine that we have this function, and this function is a nonlinear function. So this function is a nonlinear function. Now, what we know that in this teeny tiny region, this nonlinear function, can be approximated by a straight line. So how do we find out the equation of this straight line? Now, equation of the straight line, now if you look at what we have studied in high school, I have x1, y1, which is the point coordinates of the first point. I have x2, y2, which is the coordinate of the second point. I can do it something like this. I can say something like y2 is equal to y1 plus delta y divided by delta x multiplied by the basically the x1. So in other words, what I want to write this equation down as y2 minus y1 divided by x2 minus x1 is equal to slope, or dy by dx, which is equal to slope. So this equation can be written down as y2 is equal to y1 plus slope multiplied by x2 minus x1. Do you agree with me? Or I can write this equation down in terms of differential calculus. Y2 is equal to y1 plus f. So let me say like df by dx multiplied by delta x. And this is the Taylor series expansion. And I'm just retaining the first coefficient in the Taylor series expansion because that is the linear approximation. Everyone understood this? So what I'm trying to do is I'm trying to use this equation by Taylor series expansion, and I'm going to approximate this function with using a Taylor series expansion. So function is approximated as value of function at the previous point plus derivative of function with respect to independent variable at operating point multiplied by delta x. And that is the Taylor series expansion. Sometimes your function could include multiple variables. So you can have maybe the function will be comprising of x's, y's, and in that case, if you have multiple independent variables, what you do is you consider the partial differential equation. If there is only one independent variable, then it will be the full derivative. But if it's a multiple multiple independent variables, then it will be considered as a partial derivative. And this is how you would use the Taylor series expansion. And finding out the Taylor series expansion is very simple. You can use the MATLAB command Taylor, and that will give you the Taylor series expansion. Or if you have a Taylor series expansion, you can use a simple derivative. Now what I want to do is I want to take us a simple example. Say I have this spring. I have this spring, and this spring is a nonlinear spring. So this spring is a nonlinear spring. So this spring is given as maybe kx square. So I have this mass m, I have this k here. The differential equation of motion, force is equal to mass times acceleration, is written as mx double dot plus kx square is equal to 0. This equation is a nonlinear equation. Now what I want to do is, in this nonlinear equation, which one is the nonlinear term? Nonlinear term is x square. So if I want to linearize, what I want to do is, I would have to linearize this term, which is kx square. So how do I linearize this term? So to linearize this term, what I need to do is I'm going to linearize it about x is equal to 0. Please understand, you cannot linearize anywhere, you need to specify the operating point, and you need to linearize this about a certain operating point. So you can linearize this about 0, or you can linearize this about another operating point 1, or you can linearize this about some other operating point 2. Now there are two ways to linearize. One way to linearize is just take the derivative. And if you take the derivative, this derivative is going to be 2k times x. And this is the linear approximation. So what you can do is your equation mx plus 2kx is equal to 0. This is going to be your linearized expression. The other way to do it is take it kx square and then replace x with some x naught plus delta x. So k multiplied by x plus delta x, and expand this. So k, this will become x square plus this will become 2x delta x and plus delta x square, and throw the nonlinear terms. So this becomes 0. This is very, very small. Since this is nonlinear, this will be 0. This is very, very small. So this is 0. So your approximation is going to be 2 times x delta x is the approximation of kx square. And then what you do is you substitute this equation into your original equation, and you have the linearized system. Now, you can actually represent the nonlinear systems as state space in nonlinear state space. And then what you can do is you can actually linearize these systems, and once you have a linear system, you can predict the stability based on the eigenvalues of the linear system. So if you have a nonlinear system, you can linearize, then get the linear system, and then predict the stability of the linear system based on the eigenvalues. And this is something important to observe. If you see that the linear system is stable, or if you see the linear system is unstable, then your nonlinear system will be stable or unstable at that operating point. But if you find out that your linearized system is simply stable, then you cannot predict the stability of the nonlinear system. I don't know if you follow this completely, but I just want to give you this very powerful tool. This is called as Hartmann Grobmann theorem. And this is very important theorem. So if you have a nonlinear system, and you linearize, and then find a linear system. And as soon as you have a linear system, you can look at the poles of the linear system, or you can find the eigenvalues of the linear system, and then understand whether this linear system is stable or unstable. And please note that if you find the linear system is stable, then for the same operating region, the nonlinear system, the original nonlinear system, is going to be stable. If you find the linear system to be unstable in that operating point, then you will notice original nonlinear system will be unstable. But for some reason, if you observe the linear system is simply stable, you cannot predict. So cannot predict stability. So this is something that you should keep in mind. The Hartmann-Groban theorem states that the stability of the linear system near the operating point would be the stability of the nonlinear system at the operating point, as long as the eigenvalues are positive or eigenvalues are negative. If the eigenvalues have zero real part, then you cannot predict. And again, this is the technique for linearization. You can use MATLAB for linearization, or you can use the simple Taylor series expansion for linearization. Linearization can occur around a single point, or linearization can occur at an operating condition. So linearization is about a stable point, or linearization could be about the operating condition, and basically again the stability of the system can be studied by looking at the linearization. There are different practical considerations. So basically there are different types of nonlinearities. So you could have a deadband nonlinearity, you could have a hysteresis nonlinearity, or you can have maybe a saturation type of nonlinearity. And these nonlinearities, they occur in practice, and as engineers we need to understand how do we handle these nonlinearities and how do we solve the equation of motion. Now in next few slides there are some examples, and these examples come from the textbook. And what I want to do is I don't want to solve these examples because these examples are completely solved in the textbook. But what I want to do is I want to walk you through the solution of these examples. So the first example that is in the textbook, if you have the textbook, I would encourage you to take a look at that example. The first example, we have a robotic spray system, and that has an induction motor attached to the gear transmission, and that gear transmission is attached to the pump, and there is damping, there is external torque, and there is spring. And what we want to do is we want to derive the differential equation of motion. But please try to understand this is a nonlinear system. So if you want to derive this, we have to first derive the nonlinear equation of motion, then use the linearization technique that we talked about and linearize this system. So first and foremost, he's asking us, we have to comment about the model accuracy. Then we have to identify the state variables, and the state variables are motor speed, pump torque, and we have to derive these state equations using the nonlinear state model. And then we have to comment on what these parameters represent in terms of motor behavior. Then we have to look at the steady state operation, and then we have to look at derive the linear state space model, and then we have to look at how do we control this system. So this is the approximate model or the practical model for this robotic spray system, and he has given us a way to solve this problem. So first and foremost, if you look at this basic mathematical model, the gears are not going to be super duper accurate. There is going to be a backlash. There is going to be inertia that will be in the the gear transmission system. The shaft, even though we say the shaft is rigid, no shaft is 100% rigid. There will be some flexibility in coupling, and there will be some energy dissipation in the pump, and there will be some damping that will dissipate that energy. So first and foremost, we have to define these state variables. First state variable is motor speed. Second state variable is pump speed. And then we have to use the equation for power. Power is equal to torque times speed. And then actually find out the relationship for the gear efficiency. Once we derive the equation, gear efficiency equation, that actually gives us the relationship between the torque of the gear, torque gear, and torque pump. Then what we have to do is we have to apply Newton's law sequentially. And this law is P is equal to I times alpha. This is the same law that we applied when we derived the equation of simple pendulum. So I times alpha, this term is over here, and the torque term is over here. So you have torque, and you are equating the torque to the mass moment of inertia multiplied by the angular acceleration. And please note, this angular acceleration is rate of change of angular velocity. Then same thing, you have to apply the Newton's second law for the pump. You have to apply the torque, and then you have to apply the inertia forces, and then finally you have this flexible shaft that is in between the pump and the motor. So for that you have to use this Hooke's law. What does Hooke's law state? Hooke's law states that the torque is K times theta. So this is Kp. So torque is equal to Kp times theta motor minus theta pump. And if you take the derivative of torque, T dot, Kp, coefficient of spring, it's constant, but you need to take theta dot m minus theta dot p. So this is the equation. This equation is represented over here. And with that, we are ready to find out our state vector. So state vector is motor speed, torque, and pump speed. And then we have three equations, and from those equations we have to substitute, and then finally we land up with this equation. And then please note this equation, after you substitute the value of torque, you have the nonlinear equation that needs to be analyzed. And moving on, you can actually find out the equilibrium points. The equilibrium points means when omega is equal to 0, when torque is equal to 0, those are gonna give you the equilibrium points. And then what you can do is you can do the Taylor series approximation. So this is the Taylor series approximation. to find out these coefficients. And then you can substitute these coefficients and actually proceed to linearization. And this will give you the linearized state space equations. So this will give you the linearized state space equations. And I would encourage you to go through this calculation, because unless you work out this calculation, you will not get confidence. The problem seems like intimidating, very complex, but actually it's not. And in case if you're not comfortable doing Taylor series approximation by hand, please use MATLAB code, MATLAB function, Taylor, and that will do this approximation for you. You don't have to do it by hand. You can use the MATLAB function Taylor, and that will give you this. Now, again, these are some of the main concepts that are discussed in example 1, which is we have electromechanical coupling, we have mechanical damping, we have system nonlinearities, state variables, and the input and output relationship. There is a second example. Again, this comes from the textbook. And in this problem, what you have is you have the motor that is attached to a cutting tool. And then the questions are given as you have input, you have output, find the state vector, find the model, consider the steady operating conditions, and then follow the same process that we discussed earlier. The solution is given here. This comes from the textbook. All these slides are uploaded onto Canvas. I would strongly encourage you to try to work out this solution. And something that I want to show you here, an important point, is look at this nature of damping. So this is basically a sine type damping, which means whether the damping is the velocity is positive or negative, damping will always be positive. So I would encourage you to go through this development and then try to see how the solution is worked out, and then get yourself familiar with this. I would like to solve these, but let me tell you that I tried solving this example from the scratch in my earlier classes, and unfortunately the students couldn't get it because they seem involved. So what I would encourage you to do is I would encourage you to solve these examples on your own, and then in the next class I would actually go through this example line by line and give you the solution. So rather than giving the solution, what I want you to do is I want you to review these solutions on your own, and then I will work out these problems in the class. These solutions, they are from the textbook. So there are 4 problems in the textbook, and I would encourage you to look at these 4 problems. And in my next class, I would work out these problems line by line. Yeah. Chapter 2. So basically these problems, the first problem is on page number 39. So I'm going to give you this homework, insert. Workout problems, problem 2.4 on page 39. And I promise you that it may so happen that you won't be able to get the entire problem, but at least some familiarity would be good, because these problems are super fundamental. Once you understand these problems, 2.6, page 50, and 2.7, page 53. So there are multiple ways of doing this. You can try to do it with hand calculations, or try to use MATLAB. And so what would happen is, once you start solving this problem, you'll realize that these equations are super complex. And at that time, you can look at the textbook. I want you to be familiar with the process, not necessarily get the answers exactly like what they are in the textbook, but I want you to be familiar with the process, understand the steps, what they have done. Because what I'm going to do is, I'm going to give you some homework problems. So today, and they will essentially involve working out similar problems. So you please pay attention to these problems. So everyone understood? Now what I want to do is, I want to move on to the lab component of today's lesson. So for the lab component, I want to actually talk about few things. If you have access to APM monitor, I'm gonna so basically go to APM monitor. So go to APM monitor, go to Arduino temperature control. So what I want you to do is, I'm going to put this link in the chat window. I want to put this link in the chat window. So everyone, please go to this link, APM monitor, PDC, index, temperature control. That will take you to this temperature control lab. So at this point, please visit. Temperature control lab. Let me please visit. Temperature control lab. So I want you just a second. I'm trying to stack these windows next to each other. So I want you to visit this temperature control lab. And in temperature control lab, I want you to go to model. So physics-based model. And my hope is that you will actually go through this example. And in the last class, we talked about this. Now, actually, I want to show just a second. I want to show both. Okay. what I'm going to do is so I can't scroll this down. Let me see if I can scroll it down like this. Okay. So zoom. And I'm going to do share screen. And I'm going to do full screen. Sure. So I want you to go to this dynamic temperature modeling. So this is the heater model. Now I want you to get your temperature lab set up. So the first phase of the temperature control lab is to derive a dynamic model of the system with the guess value for parameters. Now in today's class, what we did, we derived some dynamical models. Now what we want to do is we want to use the concepts that we learned in today's lesson to derive a dynamical model for this heater system. So what is the advantage of this dynamical model? The idea of the dynamical model would be we will have some type of equations. Those equations we can use MATLAB to solve and understand how the system behaves. So if you look at the way this system is, there is a heater. That heater is attached to the heat sink. The heat sink is attached to the thermal glue, and the thermistor is attached to the thermal glue. So if you look at the properties of the system, you have some initial temperature, which is the temperature at room temperature. We have some heater output. So heater can supply 1 watt. There is a heater factor, which actually talks about 0.01 watt per percent of heater. So for an example, if you say 10%, then the heater is going to heat at 0.1 watt. If you say 100%, then the heater would be heating at full speed, which is 1 watt. There is something called as the heat capacity, CP. Then there is surface area. There is mass of the heat sink and the heater. And then there is this overall heat transfer coefficient. And there is something called as the emissivity. So what I want to tell you is there are 3 mechanisms of heat transfer. There is conduction, there is convection, and there is radiation. So what happens in conduction? So in conduction, the heat transfer is basically through physical connection between the elements. In convection, what you have is you have an air particle that goes around between those 2 objects that are transferring heat. And in radiation, you don't need a medium. Basically, from one object to other object by electromagnetic waves, the heat gets transferred. So there is conduction, convection, and radiation. So what we want to do is we want to come up with a mathematical model that actually describes this heat transfer phenomenon. And what we do is we use this energy balance. This energy balance is mass times Cp, which is the specific heat at constant pressure. That is a classic approximation for heat transfer, multiplied by the rate of change of temperature, delta T over dt, which is the And then you have the heat that is coming in, heat that is going out, and the heater input. So this equation can be expanded as you have a convection component, and you have a convection component, and you have a radiation component, and you have the heat generation. So basically what you do is you have this is the differential equation of motion. And in this differential equation of motion, what we do is we substitute these parameters and then try to find out how this system behaves. Now at this point, what I want you to do is I want you to open this ODE 45 code. Are you with me? Can you open this ODE 45 code? And then I want you to go to MATLAB. So students who are online, I just want to make sure that you are able to see the AP Monitor website on the left and the MATLAB code on right. Are you able to see those simultaneously? Okay. Now what I want you to do is I want you to copy this code, copy, and paste it into MATLAB. Copy this code and paste it into MATLAB. Add a space and then copy this second part of the code. So copy the second part of the code. Copy and paste it over here. So what you should see is you should have this entire code inside MATLAB. And what I want to do is I want to call this function step test. Okay. So function step test. And I can actually see it will complain. You can say end. Now save this, save as, and you can go to TC lab and then just say step test. Now what I want you to, let's go through this code line by line. So what are we trying to do? We have this heater model, and what we want to do is this heater model is a dynamical system. So this is the first order dynamical system. Remember the way we use Newton's law, force is equal to mass times acceleration. So here we are using the physics based equation to come up with a differential equation of motion. So first we are supplying the amount of heat. Then we are supplying the initial temperature. Then we are entering the time for the simulation. And then we are numerically integrating this equation. And then we are plotting the results. And please understand, this code is where that differential equation of motion. So please understand, the highlighted part is the differential equation of motion. And what I want you to do is, I want you very quickly, that's why we need to do this simultaneously. I want you to very quickly compare this differential equation here with the differential equation that is shown on the left hand side. Can you see mCp delta T? This equation dt over dt is written as this differential equation. Are you with me so far? Online students, did you understand that the differential equation that you see on the left hand side is programmed inside the MATLAB. Everyone understood this? Any questions here? Online students? In-person students? Okay, I'm gonna walk around and see if there are any questions. Everyone understood what I did? I did not write the code. This code is going to numerically simulate the single heater system. A single heater system has three types of heat transfer. There is conduction, convection, and radiation. In this dynamical system equation, you have mCp delta T is equal to U times A T infinity, that is the temperature at infinity, minus the temperature plus the radiation component. That equation is programmed over here. Are you with me so far? So which means if I supply the initial conditions and if I integrate this equation numerically, I should be able to find out how the temperature propagates. Everyone understood this? Now what I'm going to do is I'm going to run this code. So run this code and then can you see that once we run this code, we get this step test. So which means initially it starts at 30 degrees, 23 degrees, and gradually it goes all the way over here. Now, what I want you to do is, I want you to look at this heater script. I want you to look at the heater script. And the only change to this heater script is, okay, in case if you don't know where that is the same script that I showed in the last class. So please go to, I'll show you where that script is. Please go to TC Lab, folder, and in TC Lab folder, you are going to have test heaters. And in test heaters, you will have this, you just need to change one line, which is I is equal to 1005, so that the heater will not be turned off. Are you with me so far? Please make this change, everyone. Online students. Are you with me so far? Online students, go to test heaters file and go to line 29 and then make this change. And at this point, your TC Lab should be hooked up to your computer. Now, please run this. I want you to observe something. Actually, this is important. Can you see the initial temperature here is about 24 degrees. We are looking at temperature 1 because temperature 2 we are not looking at right now. Temperature 1 because we actually turned on the first heater and we'll keep it on. After some time, heater number 2 will drop down. to give it some time. Are you able to see? That's okay. So what I'm trying to say here is the result that we got from running the MATLAB script, numerical integration, shows similar trend as what we see from the experimental data. Are you with me so far? So we derived a dynamical equation. We derived a dynamical equation, and what we are doing is we numerically integrated a dynamical equation with parameters that we assume. We assume that the equation is the first order differential equation, and then we are comparing the behavior of an actual system. This is like we gave a set input, right? And you observe over the period of time that you will see the response of this system that is similar to the response that we simulated. Are you with me so far? Everyone understood this? It will take some time because it needs to stabilize. But the idea is this response, what you see, this response, what you see, is similar to the response that we generated from our previous equation. Now its heater 2 will drop down, but heater 1, so basically you will see that I don't know if MATLAB can do simultaneous processing, but let me step test. Yeah. So run this code. I will call this figure 2. So please run this code, and you will observe that this response that you see is similar to the response that you have obtained from your system. So the idea is we have this mathematical model. We numerically integrated this mathematical model, and our results compare with the experimental data. They are not exact experimental data because we assumed a lot of parameters, but still at the end, we still have some type of correlation between the experimental results and the simulated results. Everyone understood? Online students? Okay.
Sir, I'm not able to run it simultaneously, sir.
Yeah, you won't be able to do it simultaneously because I'll show you. If you want to run this, what you should do is change this to figure 2. Run
Okay.
this. Now you have this figure 2. This time is in minutes.
Okay.
Now, and then now what you do is you go to test heaters. So indicate LED temperature, and then basically here this time is I is equal to 399. So we will say this is 3000, and then you can say this is 3000, and now you run.
Okay, sir. Got it.
So you will have both these files. You will have figure 1, where did figure 1 go? And then you should have figure 2.
Got it, sir.
Oh, so Control C, step test, run, and then go to test heaters, run. So basically 5, so COM5, and then you should be able to get the same results.
Why is it?
What code do we use? Yeah, what do we do with the CISO code now? Oh, I'm just, okay, just a second. So now what I was trying to tell you is if you add a step input to the heater, then you get the response which is similar to the response that you get from the experimental results. So that's what I was trying to tell you. Everyone understood? Any other questions? So I don't understand, Hunter, your question. What do you mean by CISO code now? So CISO code is for FPE OPT. Basically, if you go to TC Lab, you have MATLAB CISO, and then what you have is you have test models. This is the code, and that actually will do the experimental determination of the first order model. So that's what it will do. Okay. Now what I'm going to do is I'm going to move on to the lab that we want to discuss today. And my suggestion to all of you would be, it's very difficult to do this lab exercise online. So if you can come to class, that will actually benefit you a lot. So that way I can walk around and explain what's going on and then kind of discuss what we are doing. Okay. Any other questions on this lab?
For the paper, do we just compare the results?
Yes, if you compare the results, you will see that the experimental data will be similar to the theoretical data. The only problem that you'll observe is it won't be accurate because our parameters that we have assumed are going to be different. Now, the next thing which I want to talk about is this is the second assignment that we are going to work on, which is if you have two heaters is a multiple input, multiple output system. Why it is called multiple input, multiple outputs? Because you have two heaters, so two inputs, and you have two temperature sensors or two thermistors. So you have two outputs. You have two inputs and two outputs. That's why this system is a multiple input, multiple output system. Everyone understood this? Now, what happens when you have a multiple input, multiple output system? One system affects the behavior of the other system. So for an example, heater number 1 is going to affect the behavior of thermistor number 2. Heater number 2 is going to affect the behavior or temperature of thermistor number 1. So basically, there is going to be a coupling between those two. Just like we saw spring mass system, since we had 3 springs, 2 masses, and these 2 masses were attached or coupled to each other by a central spring. That's why the response of first mass affected the response of the second mass. Same thing here. You have this thermistor 1 that is going to respond to heater 1 and heater 2. So what we want to do now is, if you go down, you have two actuators, two sensors, and then again the two thermistors and two heat sinks are identical. So the coefficients, the parameters are given over here. But what I want you to understand is, now you have two differential equations of motion. Have you seen this? There are two differential equations of motion. The first differential equation of motion describes the rate of change of temperature for thermistor 1. Second differential equation talks about the rate of change of temperature for thermistor 2. You have the convection, you have the radiation, but please note, you have this coupling term. This coupling term is telling you how the behavior of the second temperature sensor is affected by the first heater and vice versa. So what you have is, you have this coupling term that is showing you how the first heater affecting the temperature of the second thermistor, and how the second heater is affecting the temperature of the first heater. Now, what we want to do is, we want to look at the simulation. So again, click on MATLAB ODE source file and do the exact same thing. You can actually grab this whole code, and now you can open MATLAB. So and paste this code inside MATLAB. So copy and paste this entire code. So click get code. Copy. And you can paste this code inside the MATLAB. Paste. Then go down. Take this code. Copy. Paste this code inside MATLAB. And then I'm going to call this function double heater. Then go down, and it's going to ask you for one more end. Add this end over here. Then save as. Go to, I would just put it in TC Lab and save it as double heater. And then I would run this. I would say change folder. And then what you will see, you will notice that this is the behavior when you have a Mimo system. So the way the system is working is, initially you turn on the first heater. That first heater goes to 100%. So you will observe that this system, actually the response affects, this is the blue response of the first thermistor. But as the first heater is turned on, the temperature of second heater starts increasing. As the first heater is turned on, temperature of second thermistor goes on increasing. And after the second heater is turned on, basically the temperature of second thermistor increases rapidly. So what I want you to do is I want you to look at this Mimo system. In this Mimo system, first you have a step input. So you turn on the first heater. Second heater is turned off. So as the first heater is turned off, the first thermistor goes increasing. The temperature goes on increasing. As the temperature increases, because of the first heater, second thermistor also heats up. So you will see this gradually heating. And when the second heater is turned on, the second heater heats the second thermistor, and then the temperature of the second thermistor increases exponentially. So what I want you to do is, I just want you to basically, you can say something like, let me see, what would be the best way to, you can say copy figure, then go to a Word document or paint, and then paste. So now you have this figure. This figure is not going to go anywhere. Then what I want you to do is, I want you to go to this Mimo file. So basically go to TC Lab, add to path, all folders, then go to Mimo. And then when you go to Mimo, then what I want you to do, this is a Simulink. Just go to MATLAB. So MATLAB Mimo, and then go to energy balance.m. Go to test model.m. This is the file that you should get you T1C, T2C. Let me close this for a second. And then run this file. Oh, I think I ran CISO. I don't want to run CISO. Please run this Mimo file. So go to test TC Lab Mimo. Then go to test models and then run. Where do you get Mimo files? If you go to Mimo file, you will go here. Download MATLAB TC files for dual heaters. And now I want you to observe the system. And please compare this response with the system that we have here. So you can see this is the T2 is the measured value. T1, so you can see this blue line should correspond to this blue and black line. And as you see that when the heater is turned on, the second temperature, which is T2 measured, is heating up. So can you see that T2 is going up? And then gradually it goes up. So what I want you to observe is the experimental results from this Mimo system. They match very well with the P predicted result. So P1 is the predicted result. The predicted result comes from the solution of the differential equation. And black P1 measure that comes from the actual experimental data. And you see that these two, they match quite well. Are you with me, online students? Any questions? Any questions from online students? Are you able to get the same result? Are you able to get the data?
Do we need to do a write-up for this one too?
Yes. And please understand, here the time is in minutes. Here the time is in seconds. So it will take some time, but you'll observe that the response is similar. So at 5 minutes, the other heater will be turned on, which is about 300 seconds. Online students, are you able to get these results? Are you able to get the data? Okay. So everyone understood that this blue line, what you see on the right hand side, is same as this blue line from the simulation. But this black line, what you see over here, is the black line of temperature that we get from the actual data. Now please understand. Now I want you to observe. Initially, this blue line, this Q1, initially we turned on heater number 1. At 5 minutes, we turned on heater number 2. So even though the heater number 2 was turned off, the temperature of the second thermistor increased gradually. And there is a slight deviation, that is because of, this is the result because of the experimental and assumptions result. So we have some assumptions and there could be some experimental variation. That's why the result, the theoretical result is not exactly matching with the actual result, but it is very close. So here, if you see red line, this is when the second heater got turned on. This is when the second heater got turned on. And now you will see, since the second heater is got turned on, the temperature of the second thermistor would increase exponentially. So you will see that so this was the second lab. Any questions on this second lab? Okay, if there are no questions, I would like to assign today's project. So let me share my screen. So this is project 3. So this is project 3, right? So first, complete Mimo lab and turn in 2-page report with plots. And note observations and write clear conclusion. Second, work out following problems from the textbook. Problem don't know where it went. So project workout, problem 2.26, page 212, problem 2.28, page 213, and the last problem is problem 2.73, on page 236. So this is the assignment for this week. So let me be clear. This is our project 3. This will be due next week. I already gave an extension on the previous lab, so it's due tomorrow. So I think project 2 is due tomorrow, but project 3 will be due next week. And first, I want you to complete the Mimo lab and turn in a 2-page report with plots. And the most important thing is, I want you to observe and note down your observations. So, important part is what you learned. So you will be running the simulation, you will be comparing the experimental data, you will try to improve the simulation based on the experimental data and see how well it works. And the second part is work out problem 2.26, 2.28 and 2.73. Please understand these problems 2.26, 2.28 and 2.73. As a matter of fact, I solved 2.73 in today's class. So 2.26 and 2.28 are similar to the 4 problems that are given in the textbook that I asked you to work out: 2.4, 2.5, 2.6 and 2.7. So when we meet on Thursday, I'm going to work out these 4 problems by hand in detail. That will prep you to solve these project problems 2.26, 2.28 and 2.73. Everyone understood this?
Can you please expand the board because
You can actually take a picture of my board. So yes, I will be uploading the Zoom recording later today. But at this point, I'm going to stop recording. And if you have any questions, I would be happy to answer.